All right, back with another lab intro video. This one is on circuits again, using the exact same simulation that you did last week. You're just going to do different stuff. Last week we were more focused on stuff for one resistor. This week we're looking at multiple resistors. And so there are a couple of parts in this, and I'll try to show you exactly what's going on in it. So to start out in this lab, there are a handful of questions. If you are not sure about them coming into it, my suggestion is to just go ahead and do the lab and then come back to these, because it will probably make more sense after you've actually gone through the lab, how to answer these. But you can probably figure them out from the intro material, if you would rather just get them out of the way to begin with. So two of them are basically like kind of a multiple choice thing, and then the last one is a short answer. So when we get started here, we're using the DC construction kit again. And the first circuit that they are asking us to create is a battery with two light bulbs. There's a different figure here than what we are interested in talking about. So we'll have one battery, two light bulbs in series, which means I'm going to go from my battery to one light bulb, then from this light bulb to the next light bulb, and then back around to the battery to get a complete circuit. But I'm going to go ahead and start from the positive terminal. So I'm going to go here, and then here, and here. Remember from what we learned last week, we need a complete path for the current to flow through this circuit. I don't think there's anything. Yeah, there's nothing there beforehand. All right, so I've got my circuit set up. I've got a battery. I've got two light bulbs. And first thing we're going to do is use our voltmeter to measure the potential difference across the two bulbs one at a time. Just like last week when you're doing this, all I care about is the number. If you get a negative sign, do not include the negative sign. That just means you read it backwards. So if I look at the first bulb, you can call whichever one you want, bulb 1 or 2. I'm going to call this one bulb 1. So when I measure this here, that's not in the best spot, but if I move this a little bit, you'll see I get a voltage of 4.5 volts across this one. If I connected this in reverse, I would get minus 4.5 volts. So you're going to get the same magnitude on your voltage no matter which way you connect it. Just include the number. Don't include the sign. If you accidentally connect backwards and you get a negative sign, I don't want to see that, because that just means you connected backwards. Then I would do the same thing for my second bulb. And I get the same thing because these two bulbs are identical. If one of them was a little bit different, those numbers might be different. So that's the first thing you're doing, measuring the voltage across each individual light bulb. Then you add those numbers up, and then you measure across both light bulbs. So start at the first bulb, end at the second bulb, and you need to be on, you can't connect here because then you haven't gone through the second bulb. You have to be on the other side here. So there's my sum voltage. And then they're going to ask you to measure the voltage on the battery as well, which looks similar. So question 1, individual voltages. Question 2 is just adding those individual voltages. 3 is the voltage across both bulbs together. Then you get asked a question about how those numbers compare. The battery Then you're asked to compare numbers again. And now comes the interesting part. So what we need to do here for 7, 8, and 9 is short one of our bulbs in the circuit. So let me come back here. Let me move this guy out of the way real quick. And so to short out a bulb, we still need this path. We're not going to disrupt this path. What we're going to do is we're going to take a wire, and when I short, I'm going to connect between my two terminals here, if it will let me do it, which it doesn't look like it will. So I'm going to do this a different way. I'm going to go ahead and take two wires, one connected to one side of this bulb, one connected to the other side of this bulb, and then I'm going to connect these together. So when I did this, I've given the current, a different path to travel. It can now go through the first bulb like it was before, but rather than going through the second bulb, what's happening now is I've given it a path to go around that bulb. And you'll notice that if I break this connection here, this is what we had before I short the bulb. Both of these bulbs are lit. They're fairly dim comparatively. And then when I short this second bulb, this one goes out and the first one now is brighter. So that is what it's asking you to do here. What happens to the brightness of the bulb across which the wires are connected? That's this bulb. And what happens across the other bulb is that one. And so it's asking whether you have more or less current flow when we have this in place. Now, one way to look at this is the brightness of the bulb. You have to have more current flowing through here. Yes, you have less here, but the whole circuit is now taking, instead of the current going through both bulbs, it's going around this bulb, so it's flowing faster. You'll notice if you watch the speed at which these electrons move, when I snip this connection again, they slow down around here. So there's more current in the entire circuit, even though this bulb is seeing less current. And the reason for this is because if I'm looking at the total resistance in my circuit, when I have both of them in here, and the potential difference from the battery is seeing both bulbs, well, this has a 10 ohm resistance, this has a 10 ohm resistance, so the battery is seeing 20 ohms. Whenever I go around this bulb now, this one is not seen by the battery anymore because it just goes through these wires instead. And here I get just this bulb resistance affecting the circuit. So the battery's only seeing 10 ohms, which is why the current is higher. So if you've ever heard the phrase, current follows the path of least resistance, this is an explicit demonstration of this. Because when the current gets to this bulb here, it has a choice. It can go through the light bulb, which has a resistance, or it can go through the wire, which has no resistance. And it's going to take the path of least resistance, which means it's going to go around the bulb and through the wire instead. And this is just the nature of current flow. It's going to do that because it's basically wasting less energy going through a lower resistance path. And so it's better to go through the low resistance path when given the option. So the next part, blank page for some reason, is looking at the current in a series circuit. So when you come to part B, we're going to go ahead and delete those short wires that I put in. So I'm just going to go ahead and delete these, trash them out. So I go back to my original circuit, and then it wants you to first say whether the bulbs are lit, which they are. And we want to put our ammeter between the battery and the first light bulb. So just like last week, you have two options for measuring current. You can use your non-contact guy to just hover over the wire and record the current, or you can use the old school ammeter, this guy here, by cutting my circuit and putting this this current meter in place. So when I do that, this is the position it's asking you for question 11, between the positive terminal here and the first light bulb. So you'll see, regardless of which way I measure this, I get the same current. So in my opinion, it's better to use the non-contact ammeter so you don't have to split your circuit up and possibly mess that up. But you're free to do whatever you want here. So I'm just going to go ahead and use the non-contact meter for the rest of this part. So record the current between the positive terminal and the first bulb. You write that down, and then you're going to record the current between the two bulbs. You'll write that down, and then you're going to record the current after the second bulb, and you'll write that down. So those are the three currents that you record. Here's between the positive terminal and the first bulb, between the two light bulbs, and then between the second light bulb and the negative terminal. And you probably noticed that they were all the same, which is the way it should be for a series circuit. If I have a series circuit like this, there's only one path for the current to follow, so it can't be the same anywhere. It's got to be exactly the same at every point in the circuit. You can't have any differences when there's only one path for the current to follow. And the reason for that has to do with something called conservation of charge, which basically says that you can't create or destroy charge, you can just move it around. So if, just imagine for a second, this bulb only got 0.3 amps and this one got 0.4 amps. If there was a difference between these, what that would mean is the charge would have to be building up somewhere instead of moving through, which violates our conservation of charge. So when we have one path like this, the only possible option to not violate the laws of physics is to have just the same current everywhere in the circuit. All right, so this next part, we're going to be looking at Ohm's Law. So before we start this part, we want to quickly just look at the circuit for one light bulb. So I'm going to break this. I'm not going to reconnect this bulb right now. I'm going to just show you what you see for one bulb. So it's wanting you to look at what brightness for one bulb, and then you're going to compare that to the brightness for two bulbs. So I'm going to go ahead and put this back together. So this part here is kind of easy to miss, but it's important. So when I have my two bulbs in series, are they less bright or more bright than the single bulb? You saw pretty quickly that they are less bright. So since there is less light, there's less current. So you have a choice here. So what I want to do then is look at the resistance of a single light bulb and write it down. So I would click on this, record the resistance. Then you would do the battery voltage, record that. And then in this table, what you're going to be doing is recording the current as you add light bulbs. So if I go back and I cut this guy out, so that I'm only having one bulb in my circuit, I want to record this current, and that is 0.9 amps. I'm just going to show you two as an example of what you're going to be doing. I'm going to cut this back out and then rewire my circuit again. So now I have two, I would have 0.45, which we already measured. Not 9, 0.45 amps. And your resistance is V over I, exactly as it says here. So this would be 9 volts for my battery divided by 0.9 amps, which would be 10 ohms. You don't have to worry about the units because that's implied in the column here. So even here, you could just put 0.9 and 0.45 and it would be cool. For the second one, it's the same idea, 9 volts divided by 0.45 amps. That would give me 20. And then I would do a third bulb. So I'd have to break this here, say, bring a third bulb in, connect it in. Now they're even dimmer and my current has gone down to 0.3. So you would keep going, add a fourth bulb, record the current, add a fifth bulb, record the current, take those currents and it's your battery voltage, which if you don't touch it is 9 volts divided by the current that you measure here. That gives you the resistance that you're looking at. So you have a question about how the brightness changes, which you should have seen. How does the total resistance compare to individual resistances? So this question is saying, how does this number, this total number that I have here, say for 2, compare to the single bulb resistance that you measured up here? So 20 is greater than 10. That's how I would answer that question. 24, how does the total resistance compare to the sum of the resistances? So here you're comparing the number that you get in this table to adding up individual resistances. So in the second circuit, I have 2 light bulbs. Each one is 10 ohms. So 10 plus 10 is 20. And then you're going to compare that 20 to the number that you have here. Was the current greater or less when the resistance was greater or less? That's pretty clear even from last week. And what does this suggest about the relationship between current and resistance for things like light bulb? Are they do they vary directly? Are they inversely proportional? This is assuming a constant voltage. So if you keep V constant, but you change R, what's going to happen to the current is what that question is basically asking. So that's it. That's the second circuit lab. It, in my opinion, is pretty quick. There's a lot of space in there. You're doing quite a few measurements this week to get it done, but there's a lot of repetitiveness to it, so it should go pretty quickly. This part of building 1, then 2, then 3, then 4, then 5 takes a little time just because you have to drag all the components in, but it's pretty straightforward what's going on in there. So that's it. Next week's lab is our last one, the one that I'm going to put up next week anyway. And that one uses a Java simulation. So I will record not only the intro video where I'm narrating what it's asking you, but just a silent video where I am following through the procedure and just doing the lab for you to work off of. And that will be the last one. We're coming up pretty close to the end of the semester. So if you are missing stuff in the lab part, especially 7 and 8, those now have videos also in the modules section so that you can do those if you don't have Java installed on your computer. Any other, I've graded 7 and 8. I will probably grade any more 7, 8 submissions and Lab 9 at some point during the week this week, so you have an idea of where you're standing in lab. 7 through 12, you can technically still turn them in until we get to the end of the semester. 7 and 8, I'm not going to enforce any semblance of late policies on because it took me so long to get them up for you to be able to work on those. So even if you were to turn in lab 7 in 2 weeks, I'm not going to take anything off for that. The other labs where we're working with things that are much more traditional, things that pretty much everyone has no problems running, those ones I might take a little bit off if I get stuff submitted after I actually grade them. But so long as it's in before I actually do the grading, I'm not going to take any points off. We're in a weird time where I don't know what your jobs are. So I don't know if you're working in a grocery store, working extremely heavy hours, and it's hard for you to find the time to get to this stuff. And I don't want to punish someone for that, especially if you are running into issues with work. I would say go ahead and contact me so that way I know what's up, and I'm totally willing to be a little bit flexible on that so long as you're getting stuff in before the end of the semester. I'm about to go into recording the chapter 12 stuff pretty soon, and I'll get those up tomorrow, which is Monday. At some point, I'll get them up and up in YouTube so that they're processing, work on the pages and everything, and get those up in the course for you. And I guess that's really all I have to say about this. So, yeah, good luck with this. I think this one's pretty simple, just like last week is not really that bad. Next week's is a little bit more conceptual than these two, which are, there are a handful more measurements for you to do. So there's a lot more short answer next week, and that's about it. So good luck, and